So in the previous video, we looked at, we noticed how in Chapter 5 we were introduced to alkenes, and in Chapter 6 we were introduced to a bunch of reactions. The reactions of alkenes. What general class of reactions do we have with alkenes? What general class of reactions do we have with alkenes? Usually addition reactions, right? Electrophilic addition reactions. So we looked at those, and then at the end we had a ton of reactions in Chapter 6. And we said, all right, well, because we have these reactions, we're going to have to start thinking about synthesis. What can we do with the reactions, right? So we did a video on synthesis, introduction, example 1, example 2, and now we'll do example 3. And we said, all right, at the end of Chapter 6, we had a ton of reactions. What's it mean? How can we deal with those? Now we're here at the end of Chapter 7. Okay, as we predicted, there's another section on introduction on multi-step synthesis. Now it's called Introduction to Multi-Step Synthesis. Okay, so she goes through, I think, a pretty good job of what a multi-step synthesis looks like and what you ought to be thinking. It's a little bit overwhelming maybe to students to start thinking about this in terms of retrosynthesis and so on. So that's why I'm doing these videos, and also providing perhaps an alternate to her method, and as thinking in terms of reaction classes and how we think about these, look at the beginning and ending products and decide what has to get done. So let's do another example. I illustrated this pretty well, I think, with example 1, not so much with example 2. That was a little bit too simple to do it with this. And let's do another one, example 3. So what I'm doing is I'm taking one from the book. I'm not just making one up. Number 49. Okay, and it doesn't matter which one we do. I say let's do A. Okay, so that's acetylene to 1, 2, 3, 4, 5, 6. Acetylene, and she wants us to go through a multi-step synthesis. We don't know how many steps I'm doing that just to remind myself. 1, 2, 3, 4, 5, 6. Okay, and it looks like at the end of that 6, the second to the last, there's a carbonyl carbon, okay, or a ketone. So this is going to look a little upside down, but all right, let's do that. Now let's look at the question stem. That's the synthesis she wants us to do. Let's look at the question stem. It says, show how each of the following compounds could be prepared using the given starting material, so we've got to use acetylene, any necessary inorganic reagents, and any necessary organic compound that has no more than 4 carbons. So we can bring in anything else that's got 4 carbons. All right, so what we're going to do is we're going to ask ourselves again, what's the functionality in these? I've got a triple bond over here. That's my functionality. And over here, I've got a ketone, carbonyl carbon. So we're definitely going to be changing some functionality. Right? And I also have only 2 carbons over here and 6 over here. So if I'm going from 2 carbons to 6 carbons, I've got to add 4 carbons. Right? I might add them all at once. I might add them at different steps, but I've got to add 4 carbons. Now the question is, Sam said I can introduce 4 carbon compounds so long as I do it. I can introduce new carbons so long as I do it with no more than 4. Okay, but that's fine. That's all I need to do is add a 4 carbon compound. All right. Now we need to ask ourselves, how can we make carbonyl carbons? Let me just review the reactions with you real quickly. We have a reaction that looks like this, an internal carbon, and water, okay, and that gives us that's one reaction we've got. Okay, the problem is that's got to be symmetric, so that's not going to work here because this is not symmetric, right? Do you agree that if I had the carbon here too, it would be the same thing, right? So it doesn't matter if it's there or there. Okay, we had another reaction where we could do, say, didn't do that on purpose, 1, 2, 3, 4 carbons. Okay, H2SO4 and mercury sulfate, mercury 2 sulfate really, right? And that would give us 1, 2, 3, 4. That'll work, and that's a terminal one. So we can force it to the end. Okay, and we use this to make methyl ketones. Right, we do this to make internal, all ketones are internal, so let me not say internal ketones, let me say internal alkynes. It doesn't work with the terminal alkynes like that one. Okay, and then the other way that we've got is we can do with a terminal alkyne, we can do, oops, it's not the right angle, but suppose it is 1, 2, 3, 4. We can do BH3 and THF and hydroxide, hydrogen peroxide, and water. 1, 2, 3, 4, and we can make, oops, an aldehyde. Okay, so those are the reactions, the ways that we have of making ketones or carbonyl carbons. All right, can you see which one of these we're going to want? Okay, it's definitely going to be this one here. All right, and then we've got to make carbon-carbon bonds, and I think the only way we have to make carbon-carbon bonds right now is that hydride and R Br, which is going to give us that, right? Acetylide, which is perfect. It's perfect because we can make that first, and then we can have a terminal. We can make this first, and then we'll have a terminal alkyne, which we can oxidize using that stuff right there. Okay, so it's a two-step reaction. Let me redraw it down here. Goes to 1, 2, 3, 4, 5, 6, and that goes to 1, 2, 3, 4, 5, 6, which is the same thing as I have up here. Okay, and that's our synthesis problem for this. So it's 1, it's hydride. 2, it's 1, 2, 3, 4. Right, 4 carbons. And then this one over here is simply mercury sulfate. H2SO4. Mercury sulfate. We're actually adding water to this, right? We're adding it's two H's and an O that we're adding to it. So let me put it like that. And there's our solution. Okay, so again, what we did was we first of all went through and said, what's the difference between the beginning and the end? What's the difference between the beginning and the end? Number one, we're going to have to introduce a functionality, or rather, not introduce it. We have functionality. We have more functionality over here. We can simply change functionality. We looked at that functionality and said it's a carbonyl carbon. Well, how do we know? What ways do we know that we can do that? And these 3 reactions came to surface. Okay. And then we said, all right, now that we know how we're going to change our functionality, what else is different? And that was, this had 2 carbons and this one's got 6. So we're going to have to add a carbon-carbon bond. And that's good because the only way that we knew to make carbon-carbon bonds at this point in the semester was to use acetylene. So both of them required acetylene. That was definitely the middle point, and here's a beautiful solution for that. Okay, I'll do another one from that problem set on request. I'll probably do one, I guess, even if you don't ask. Hopefully that's helpful.